All right, so thank you. Welcome everybody to today's SICE seminar. So I'm very happy to welcome Dr. Christine Allen-Blanchette. So she is coming to us from Princeton, where she currently is a postdoc working with Naomi Leonard. I'm going to read her little bio here off to my sides when you see me looking over this way. So she did got a dual Bachelor's of Science degree in Mechanical Engineering and Computer Engineering from San Jose State. She then did her PhD in computer science together with a master's in robotics at UPenn before moving on to Princeton. She has several wonderful awards, including the Princeton Presidential Postdoctoral Fellowship and an NSF Integrative Graduate Education and Research Training Award. So she is going to talk to us today about some of her work, and rather than me introducing her work, I'm going to let her do that because it's her work. So Christine, welcome, and the floor is yours.
Thank you. Thank you, Sean. All right, so thank you, very much for the introduction. And again, my name is Christine Allen-Blanchette. I'm excited to share some of this work that I've done with collaborators about embedding prior knowledge of dataset symmetries into neural network architectures. And along the way, if there are any clarifying questions, I'm happy to receive them. And at the end, I absolutely look forward to thinking with you all about future directions. So the talk is titled Leveraging Dataset Symmetries in Neural Network Prediction, but this idea of using prior knowledge of the dataset structure is certainly not a new idea. So it's also been called using physics-based priors and using domain knowledge. And classical convolutional neural networks were actually designed with the translational symmetry of 2D images in mind. So classical convolutional neural networks are used in various image prediction tasks, perhaps most famously for image classification, which asks which of a set of predefined objects is present in the input image. So in the image shown, the input image is an image of the car, and the set of predefined objects includes a car, a truck, a van, and a bicycle. So classical convolutional neural networks map 2D image inputs to outputs by applying convolutional filtering and nonlinear operations in an alternating sequence. Within the network, the intermediate representations are determined by convolving the previous representation with a set of filters and applying a nonlinear transformation. The set of filters used is different for each intermediate representation, and the values of the filters are learned by optimizing a cost function that penalizes dissimilarity between the network output and a desired output. And the resulting network can model highly complex relationships. Okay, so in the case of classification, the desired output is a specific class label. A good classifier will produce the correct label despite variation within the class. So within the car class, it might be a blue car or a red car, or a car on the right of the image or a car on the left of the image. And in all of those cases, our classifier should output the label car. So that last idea, that no matter how we shift this car in the image, the classifier should be able to recognize it. That's this translational symmetry of these tasks. And part of the reason classical convolutional neural networks have such strong performance in image classification is because translation equivariance, or sometimes we'll call it shift invariance, it's built into the convolution operation. Okay, so what about other transformations? So this question of other transformations is something that I've really been thinking about, continue to think about, and has motivated the work that I'll share today. So if we think about our collections of images, we don't just see translations in those images. We also see rotations and scaling And when we have engaged with, our physical world, we're thinking about objects or object models that are transformed by 3D rotational symmetries. And then thinking beyond image classification to video prediction, we're expecting that equations of motions govern the other underlying dynamics. So classical convolutional neural networks, they weren't designed for any of these settings. They were expressly designed to take into account the translational symmetry of images. That shifting an image doesn't change the information in that image. In the next couple slides, I'll review some of the mathematics necessary to adapt classical convolutional neural networks to other symmetry groups. I'll provide a few examples, and then I'll shift focus to examining how the structure of dynamical systems might be embedded into neural network architectures for physically plausible video prediction. All right, so let's think about planar convolution. Returning to our classical convolutional neural network example, the animation on the right here depicts planar convolution. So we've seen this before, perhaps a gray filter shifting over a blue input image. And at every location, the value of this green output is the product of the gray filter and the element-wise product between the image and the filter. So this process is planar convolution. And every time we're translating this filter, we're applying the action of the 2D translation group. So since this idea about a group and that of a group action will come up again, I'll just give a definition here. So a group is a set together with a composition operation. The composition is associative, and the set contains an identity element, inverse of every element in it, and it's closed under composition. And the group action describes how a group transforms an object. In our planar convolution example, we consider the 2D translation group. An element of the 2D translation group can be written in matrix form like this. U is the shift in the X direction, V is the shift in the Y direction, and this group, this matrix group, is closed under matrix multiplication. And we also have that every matrix element has an inverse. So an element of the 2D translation group, it acts on a point in a plane by matrix multiplication. And then the result is a translated point in the plane. So our point xy has been translated to x plus u and y plus v. The convolution shown on the right, the animation again, is showing a repeated application of the 2D translation group action. So then the convolution of functions is an operation between functions defined on a group. And in classical convolutional neural networks, again, the group that we're thinking about is the 2D translation group. So often the function g, which is colored in gray in the animation, it's called a filter. And f is what's colored blue in the animation, it's called an image. And then this part of the animation colored green is the output of the convolution. So convolution on the 2D translation group is shift invariant or equivariant to planar translation. That is, if the blue image shifts, the green output will shift similarly. And so we can see that that's true by considering the equation for convolution in the plane. If we shift the input, f, I'm using this blue f to denote the shifted input, which is the same as our original f, except that we are offset by r in the x direction and s in the y direction. After a change of variables, mapping U plus R to A and V plus S to B. We see that the shift in our input results in a shift in our output. So this shift in variance or equivariance property of convolution, which is inherited by convolutional neural networks. The 2D translation equivariance of convolutional neural networks is part of why they work so well for image-based tasks. Okay, but again, what about equivariance to other kinds of transformations? Okay, so some transformations like 2D rotations can be represented as translations because they commute. And the idea that they commute just means that the order in which 2D rotations are performed doesn't change the outcome. So I can show you with my phone. It's a little bit blurry, but you can see. If I rotate my phone, for example, while keeping it pointed at me, so keeping it pointed at me, that's a 2D rotation. And I can rotate it clockwise for me, 90 degrees, and then counterclockwise, 180 degrees. And I get the same result as if I first rotated it counterclockwise 180 degrees and then rotated it clockwise 90 degrees. So if all of the data that we have just vary by 2D rotations, we can perform a change of coordinates and the 2D rotations will appear as translations. And that's nice because then we can apply a classical convolutional neural network to process the data and the output will be equivariant to transformations of the input. But in perception, robotics, and control, we're often interested in objects that transform in more complex ways. For example, 3D rotations, which are not commutative because the order in which they're performed can change the outcome. I'll show on my phone again. All right. So if I rotate along the long axis, 90 degrees, and then the short axis, 90 degrees, the back of the phone is facing you. But if I rotate along the short axis, 90 degrees, and then the long axis, 90 degrees, the back of the phone is facing the wall. Hopefully you can see this. Okay. And then it's because the 3D rotations are non-commutative group, they can't be represented as translations. And as a consequence, 3D rotational symmetry can't be preserved using a classical convolutional neural network architecture. So non-commutativity isn't just a property of groups acting on points in higher dimensions. For example, a situation where we have this robot and we want it to go out into the world and recognize the object shown here. And we'd like it to recognize that object, even if the object is rotated in the plane. And then we'd also like it to recognize the object if that object is far away and it looks like it's scaled and translated. So together, these transformations, the translations, the rotations, and scaling in the plane form the 2D similitudes, which is a non-commutative group. So my work, the Polar Transformer Network, introduced a convolutional neural network that is equivariant to Sim2 transformations. So there are a couple things that make designing a convolutional neural network with Sim2 symmetry challenging. And first is the group is high dimensional. So classical convolutional neural networks perform convolution on the 2D translation group, which is 2-dimensional. And Sim2 with a scaling parameter, a rotation parameter, and then 2 translation parameters is 4-dimensional. The second thing is that the group is non-commutative. So here I show the composition of 2 elements in Sim2. And if I compose them in the other order, this top right term would change, and specifically to beta are psi u plus v. So even if we had, the compute to do a 4D convolution, when we went to implement it, because of the non-commutativity, we would encounter the additional challenge of computing convolution with a filter that's changing shape. All right, so then the observation that informed the design of our network is that Sim2 is a semi-direct product of the 2D dilated rotations. That is the group of 2D rotations and isotropic scaling, and the 2D translations. Recognizing this, we have that the 2D dilated rotation group, a quotient group of Sim2, is a lower dimensional space. It's only 2-dimensional, where convolution of functions is equivariant to Sim2 transformations. So that's great. And then there's an additional bonus that the 2D dilated rotation group is commutative. So then there exists a change of coordinates that we can use that would let us do a 2D dilated rotational convolution using the tools we already have for 2D translational convolution. Okay, so how does this insight translate to network design? Well, the polar transformer network is a 2-stage network. The first stage can be seen as learning the quotient projection from Sim2 to the 2D dilated rotations. So given an input image, this stage of the network predicts the translation offset for the object of interest. The predicted translation offset is used to center the input image. And the result is an image transformed by just the 2D dilated rotation. Since the 2D dilated rotations are commutative, there's a change of coordinates, specifically a change to log polar coordinates, by which the 2D dilated rotations present as translations. So the image here shows the new representation of the input image after centering and a change of coordinates. In the second and the final stage of the polar transformer network, the new representation is classified using a classical convolutional 2D translational convolutional neural network. Because the new representation is because in the new representation, Sim2 transformations present as 2D translations, a classical convolutional neural network can be used to generate equivariant or shift invariant representations with respect to the Sim2 transformation group. Okay. So let's see how it all plays out. The results show that building in Sim2 symmetry does in fact improve performance with respect to multiple metrics. So the table shows the prediction error of various networks on the Sim2 MNIST dataset. Sim2 MNIST is a variant of the MNIST handwritten digit dataset, where each example is generated by transforming an MNIST digit by a Sim2 transformation and then peppering the background with clutter. So these are a few examples from that dataset. In the table, network names appended with big are bigger networks, and those appended with small are smaller network, where bigger and smaller are with respect to the number of parameters in the network. The prediction error of a classical convolutional neural network is highlighted here. And note that lower prediction error corresponds to higher accuracy, so lower is better. The polar CNN has the same architecture as the classical convolutional neural network, but all the inputs are transformed to log polar coordinates about the image origin. So that's without predicting the object centroid. We see that this network has worse performance than the classical convolutional neural network.
Can I ask a question real quick?
Yeah, please do.
So the big versus small, would it be right to assume that the three bigs are all approximately the same size, same number of parameters?
Approximately.
Yeah. And then in yours, you had those two pieces which did those two tasks. Did you train them separately or as an end-to-end training?
It's an end-to-end training.
Okay, so that it's just a structure that you designed to do what you think it should do, and then the training takes care of the parameters that should do it from end to end. That's what I said.
The structure, I think that's, yes, I think so.
All right, great, thank you.
It's just the structure that's designed, and then it's still end-to-end training. That's what you said, yes?
I think that's what I said. Yeah, I didn't understand myself either. So.
All right, cool. Yeah, I think we're on the same page there. So the harmonic network is a convolutional neural network with filters that are constrained to be rotationally equivariant. And this network outperforms the classical convolutional neural network, which is equivariant to 2D translations, but not to 2D rotations. And then finally, our network, the polar transformer network, outperforms all other networks by a significant margin. And since it's designed explicitly for Sim2 equivariance, it has superior performance, even with a drastic reduction in network size. So here, again, I think we're showing something that had to do with your question, Sean. And then because the representation space can be mapped to the space of 2D translations, the improved classification performance and reduced model size come with only a moderate increase in computation time.
Can I ask a question? I mean,
yes,
going
please.
back to that table, I mean, it looks like it has way more parameters than anything else.
Okay, so the one that I hope to highlight here is R's small, which has, we can do both. So R's big has lower prediction error than other networks. It does have more parameters, slightly more parameters than the classical convolutional neural network. That's true. If we highlight R small, the prediction error is significantly smaller than other networks, not the bigger one with the architectural intervention. But it does have many fewer parameters than, I'd say it has many fewer parameters than other networks.
Okay.
And I think that's what I'd like to highlight here.
Okay, all right. Except for HNet, maybe.
Yeah, just a few fewer. That's correct.
Okay.
But the reduction in computation time is here. So we still are outperforming a bit. But yes, I agree. Okay, so I have to say that I do really enjoy the audience participation. That actually makes me very excited, legitimately excited. But I also am on Zoom where I can only see 4 people at a time. So if you just help me and just tell me your name, that would be great. When you say something, that I would appreciate that. Thank you. All right, great. So just to summarize, the polar transformer network is a convolutional neural network designed for equivariance to Sim2 transformations. And although Sim2 is a high-dimensional non-commutative group, by examining its structure, a lower dimensional space equivariant to Sim2 transformations was identified. So this was the 2D dilated rotation group, which is a quotient group of Sim2. And then because the 2D dilated rotation group is commutative, we could do a change of coordinates, which allowed for processing with a classical convolutional neural network architecture. Okay, so.
Sorry, this is Sean again. I want to interject here. So did you sort of verify that intermediate stage, that it actually was doing the centering? If you sort of look at the results at that stage midway, that you see the data is all centered? And
yeah, so we do see that. So this, I tried to highlight that in this image here, that we are actually finding not the center of mass of the image, which could happen, where you just take the average of all of the object and all the clutter, but we're actually finding the object centroid.
Great, thank you.
Yeah, absolutely. Okay, so it turns out that we can use the same strategy when our data are not 2D images. So perhaps now we have this robot and it understands that this shape here is a chair. And we want it to be able to recognize this chair from any other angle. So this requires that the representation our robot learns is equivariant to 3D rotations. So in my work learning SO3 equivariant representations with spherical CNNs, we introduce a convolutional neural network that's equivariant to SO3 transformations. All right, so the challenges of designing a convolutional neural network with SO3 symmetry are similar to those encountered in the previous setting. So first, the group is high dimensional. So here is an element T of, an element T of SO3 parameterized by alpha, beta, and gamma, and shown in the matrix product representation. So alpha, beta, and gamma correspond to angles of rotation about the Z, Y, and X axes. An example of how T might transform an object is shown here. The cube on the right is first rotated about the X axis, and then the Y axis, and then the Z axis. Oops, X axis, Y axis, Z axis. The high dimensionality of SO3 means computing a convolution is more computationally expensive than it would be for the 2D translation group. And then in addition, if you remember from the phone demo, the group is non-commutative. We can see this if we just expand. The sound in the background is my dog dreaming. Sorry. Okay, so yes, so from the demo, we saw that SO3 is non-commutative. And we can also see this if we expand this matrix product. Almost every entry in this matrix would change if we changed the order of the rotations. But we can use the same strategy that we used in the previous example. So first, identifying a quotient space. The quotient space provides a lower dimensional space where the convolution of functions is equivariant to the higher dimensional group. And then find a computationally efficient way to perform convolution on the lower dimensional space. Okay, so returning to our matrix product representation of the 3D rotation matrices, we see that the 2D rotation group, denoted SO2, is a subgroup of the 3D rotation group, which is denoted SO3. And then the quotient of SO3 and SO2 is the two-sphere. So while the two-sphere itself is not a group, it can be, and it cannot be mapped to the 2D translations. Functions on the sphere admit a Fourier decomposition that allows us to compute convolution using pointwise product in the Fourier domain. So as you'll recall, a function on the circle, that is any periodic function, can be expressed as the linear combination of Fourier basis functions. So the animation shows a periodic function f in red, which is decomposed into a linear combination of simpler functions. Simpler functions are the Fourier basis, which are shown in dark blue. And then the periodic function f in red can be reconstructed as the combination of the Fourier bases with combination coefficients f hat which are in light blue. Okay. So as you'll recall, the convolution theorem gives us the convolution of functions f and g as the inverse Fourier transform of the pointwise product of the Fourier representations. Similarly to how a function on the circle can be expressed as the linear combination of Fourier basis functions, a function on the sphere can also be represented in terms of a Fourier decomposition. And in this representation, a kind of convolution can be performed by multiplication of Fourier coefficients. Okay, so how does this insight translate into network design? Given a 3D model, a spherical representation of the 3D model is generated by raycasting. The network maps the spherical image input to an output by applying spherical convolutional filtering and nonlinear operations in an alternating sequence. Each layer of the network, only 4 of which are shown here, is the result of a spherical convolution of the previous layer with a set of spherical filters followed by a nonlinear transformation. The spherical convolution is computed as the inverse Fourier transform of the pointwise product of Fourier coefficients. The set of filters used is different in each layer, and each of the intermediate representations is equivariant to SO3 transformations. The results show that building in SO3 symmetry does in fact improve performance with respect to multiple metrics. The table shows the prediction accuracy of various networks on the ModelNet 40 dataset, which is a standard dataset for 3D object classification. The first column shows prediction accuracy when 3D object models in both the training set and the testing set are transformed from their canonical orientation by azimuthal rotation. So that's a rotation about the z-axis prior to neural network processing. So the training data set and the testing data set were both transformed by azimuthal rotations. So the second column shows prediction accuracy when the training and testing data sets are transformed by arbitrary SO3 transformations prior to processing. And the third column shows prediction accuracy when the training data set is transformed by azimuthal rotations, and the test data set is transformed by arbitrary SO3 transformations. This experiment reveals whether representations learned in the presence of azimuthal rotations are useful for prediction in the presence of arbitrary SO3 transformations. For each experiment and approach, the table shows the prediction accuracy, so lower is worse. The PointNet is a neural network that operates on point cloud data. The neural network is invariant to point cloud permutations, but not to rotations. And when trained on inputs transformed by azimuthal rotations and tested on inputs transformed by arbitrary SO3 transformations, the performance drops considerably. In the volumetric approach highlighted here, a 3D object is represented as a voxel grid, similar to these. The voxel grid is processed using a 3D translational convolutional neural network, which embeds the 3D translational symmetry, but not the 3D rotational symmetry. And then without the 3D rotational equivariance, the network performs poorly on observations that were not seen during training. In the multi-view CNN approach highlighted here, a 3D object is represented as a collection of 2D images rendered from different viewpoints. A 2D convolutional neural network processes each image, and the resulting feature maps are combined to produce a final 3D object descriptor. The aggregation of feature maps produces an approximately SO3 equivariant descriptor. By choosing an input representation that is itself SO3 equivariant and explicitly embedding SO3 equivariance into the neural network architecture, the SO3 equivariant CNN outperforms all other approaches when presented with inputs in previously unseen orientations. This is achieved with a drastic reduction in the number of network parameters. And with an input representation that's much smaller than MVCNN. So to summarize, the SO3.
Can I interject again? Sorry. Could I get you to go back to that table? I was just curious. In the previous example, on the sim setting, you showed the increase in the number of parameters in your network did lead to increased performance. Did you see a similar thing here? If you used a much larger network in your structure, did you get improved performance?
Oh, I might have a slide. Maybe I can come back to that.
Sure, of course, yeah.
All right, thank you. Okay, so I'll go ahead and summarize here that the SO3 equivariant network is a convolutional neural network that was designed to have equivariance to SO3 transformations. And although SO3 is a high dimensional and non-commutative group, by examining its structure, a lower dimensional space equivariant to SO3 transformations was identified. So this was the two-sphere, which is a quotient space of SO3. And because the two-sphere admits a Fourier decomposition, convolution can be computed in an efficient way using the pointwise product of Fourier representations. All right. Okay, so all the way until now, sorry. I've described why prior knowledge of dataset symmetries can be useful in the design of neural networks for classification. But prior knowledge of dataset symmetries is also useful for understanding, predicting, and controlling dynamical systems. The equation shown is often used to describe a dynamical system. Here, X describes the system state, and F is the instantaneous change in the system. In order to interact with the pendulum in the image here, a robot needs to learn a representation of its underlying dynamics. My work, LagNet VIP, considers systems with dynamics described by the Lagrangian. The network learns a low-dimensional representation of the dynamics underlying an image sequence by leveraging the Lagrangian formalism. The Euler-Lagrange equation shown here provides the equations of motion for the system, which are used to predict future system states. Here, Q are the generalized coordinates that describe the configuration of the system. Q dot are the generalized velocities. Tau are the generalized forces, and L is the system Lagrangian. Before detailing the architecture and the training procedure, I'll just review a couple aspects of Lagrangian dynamics. So Hamilton's principle of least action states that motions of a mechanical system coincide with the extremals of the functional S, that is the time integral of the system Lagrangian. And a corollary of this theorem is that the evolution of the coordinates, the generalized coordinates, which describe the configuration of the system, is subject to the Euler-Lagrange equations, which can be derived by considering the extremal of S. When the system Lagrangian is given, we can compute the equations of motion by application of the Euler-Lagrange equations. For example, given the Lagrangian L, where kinetic energy has quadratic form, applying the Euler-Lagrange equations gives these equations of motion. Recall that the summands in this equation are commonly referred to as Christoffel symbols. Lagnet VIP learns a low-dimensional representation of the dynamics underlying an image sequence by leveraging the Lagrangian formalism. The system Lagrangian is assumed to have the given form. The inertia matrix M and potential energy V are parameterized by neural networks. And dynamical updates are explicitly computed within the network using the noted form for the equations of motion. Lagnet VIP depicted here is trained on observation sequences where each observation consists of 3 images. An example of a pendulum sequence is shown here. Each 3-image observation is shown in RGB. The arm of the pendulum begins up and to the left of the fixed point and then swings down without quite reaching the downward pointing position. The encoding network E learns to compress the input observations to a low-dimensional representation ZT. This representation is treated as a state space representation. The decoding network D learns to reconstruct observations from the low-dimensional state space representation. And the function F computes the dynamical update using the inertia matrix M and potential energy V, parameterized by neural networks. The encoding matrix, the encoding network E, decoding network D, inertia matrix M, potential energy V are all learned simultaneously in optimization. Once trained, Lagnet VIP predicts future observations by taking an initial observation and embedding it to a low-dimensional state space representation ZT via the encoding network E. From ZT, the dynamical update is computed using the Euler-Lagrange equations and the learned representation of the inertia matrix M and potential energy V. And this computation is denoted F. The dynamical update ZT dot and the state space representation ZT are combined by Euler integration to produce the next state prediction ZT Z hat T plus 1. Finally, Z hat T plus 1 is decoded using the decoding network D to give the final predicted next state observation. Predicting farther into the future amounts to recursive application of F in the low dimensional space. The model is trained by optimizing a 3-component loss function. The total loss is a To compute the auto-encoding reconstruction loss, an observation is encoded by the encoding network E, then directly decoded by the decoding network D, producing a reconstruction of the original observation. The autoencoder reconstruction loss is the dissimilarity between the input observation and its reconstruction. To compute the dynamics reconstruction loss, an observation is propagated through the network, producing a predicted next state observation. The dynamics reconstruction loss is the dissimilarity between the next input observation and the predicted next state observation. To compute the latent similarity loss, a sequence of observations is encoded by the encoding network E, producing the low dimensional sequence ZT through ZT plus N. By recursive application of F, the predicted next states z hat t plus 1 through z hat t plus n are computed from the initial low-dimensional state zt. The latent similarity loss is the dissimilarity between the low-dimensional sequence zt plus 1 through zt plus n and the predicted next states z hat t plus 1 through z hat t plus n. To investigate the contribution of each term, we performed an ablation study. For the observation sequence shown, the full loss function can recover the in-sequence observations well and extrapolate plausible observations beyond the bounds of the input sequence. Without the dynamics reconstruction loss, performance is poor. This may be a consequence of small perturbations in the latent space producing large perturbations in the image space. Without a mechanism to ensure trajectories in the latent space are close, they likely won't be, and without the latent similarity loss, it may be that the model learns a many-to-one decoder that only works in the region of the input sequence. Without the autoencoder reconstruction loss, results are good, but they're not as good as when all components of the loss are used. So to summarize here, LogNet VIP is a neural network designed for physically plausible video prediction. The low-dimensional state space representation and system Lagrangian are learned simultaneously. Future states are predicted using the learned equations of motion, which are explicitly formed within the network. And with success in modeling a simple pendulum, we look forward to considering more complex systems. So in each of the works that I presented here today, the symmetries of the data played an important role. Taking this structure into account in neural network design can lead to improved training efficiency and accuracy, better generalization, and greater interpretability. So the convolutional neural networks I described in this talk incorporate global symmetries. So in the future, we're excited to consider local symmetry transformations. We're also looking forward to using LogNet VIP, a neural network that learns physically interpretable quantities underlying an image sequence for control. And finally, a direction that I am very excited about is the direction of learning symmetries from data. So it's been a pleasure to share this work with you today, and I can take any questions. Thank you very much for your attention.
Okay, thank you. Let's thank in the virtual way for this great talk. So the floor is definitely open for questions if people have any questions for Dr. Allen-Blanchette. Feel free to just unmute yourself and chime in. There's no reason to be kind here.
Hi, Christina. This is Yanis. Thank you. I enjoyed your talk. If I can ask a question, I wonder, so whether you have compared, particularly in the earlier part of the work, you have compared to what happens if you use more sophisticated neural network architectures like ResNet or even more recent architectures. My understanding, and this is not really my area, is that they are relatively resilient to a relatively small perturbation. So small rotations of the image can be handled. And by small, I don't mean epsilon small. I think, rotations on the order of, 10, 15, 20, even more degrees can be handled by these types of architectures, even though they may not have embedded, as you have done in your work, the rotational invariant characteristics. So that's the first question, and maybe a second question, and you can sort of decide how exactly to prioritize them. in the SO3 work that you mentioned, again, it's a similar question. So from a robotics perspective, do you think that one would encounter such significant rotations, or, you know, for a specific robot, it's sort of sufficient to, you know, capture images from, you know, several trajectories of the robot, and then even training a more traditional deep network architecture could still do a decent job in terms of detecting or classifying these types of images?
Oops. Okay, so I think that there's like sort of a common theme among these questions about, isn't it good enough to use some of our very powerful architectures that do a fairly good job in a number of cases? And I think the answer to that likely depends on, so I have to say that I don't know well, we'll say this, and then please offer some counter if you feel it's appropriate. I think that there are two things. One is that building in invariance to particular transformations without architectural design, I think a lot of times we get that flavor from augmentation. So I think you may have even sort of hinted at that by talking about, if you have enough trajectories, then you get something that's good enough. And yeah, I think that that's true. But I think in particular with robotics applications, getting more data can be expensive in terms of time, and even expensive in terms of, you know, using your hardware perhaps. So maybe in an effort to avoid that additional expense, it makes sense to design a neural network that has the symmetries that you're interested in, that you are quite sure you'll encounter in your applications, to already be invariant to those transformations. So this is like my plug.
Yeah, I don't disagree with that. Actually, I very much like the approach. What I'm perhaps hinting is that it could be interesting to, you know, compare the two. So take, let's say, a more traditional architecture, augment the data by essentially inserting in the training set many different types of rotations. Then my guess is that, you know, the network would be able to do fairly well, more traditional architectures, but yours may be able to do equally as well with a much smaller training set, and sort of understanding that advantage in terms of the time that it takes to train and the size of the training set, that could be an interesting selling point.
Yeah, you know, and I'm very excited actually by this last point as well, about thinking about the size of the training set. So this is actually something I'm working with a student who's very interested in trying to figure out smart ways to design your data set that basically gives you the most bang for your buck. And I think perhaps there's like a relationship between what you're saying about exploring how data set size, how the size of the data set changes with different architectural interventions. Is this kind of close to what you're saying, Yanis?
Yes, yes.
Wonderful.
Yes.
Thank you.
All right, thank you.
I have a question, just a couple of questions about the way you were using words. You talked about SO3 being a higher dimensional group or a higher dimensional object. So I guess if by high dimensional, you mean it's 3 instead of 2,
yeah,
that's fine. But did you mean something more than that?
No, just 3 instead of 2.
Oh, okay.
3 instead of 2, because I think like if we clock it, if we see how much it adds to computation, it ends up adding quite a bit, even though, you know, if I say 3 and 2 and I'm using high, yeah, I can appreciate that was kind of odd.
The other thing I didn't quite get, I think, is you were making some sort of equivalence between things that are translationally invariant in the plane and things that are rotationally invariant. And rotations and translations are just way, way different kinds of objects. And I'm confused by that. I mean, translations are this non-compact subgroup, if you want to put it in your group theoretical terms, and rotations are compact, and if you're just doing them in the plane, it's just a one-dimensional thing. So I didn't quite get that equivalence you were making.
Yeah. So the similarity that I was going for was that if you that 2D rotations in particular are commutative, and that is the similarity that I was trying to latch on there. That the 2D translations are commutative, and the 2D rotations are also commutative. And then if we think about, so are you able to see my screen still?
Yeah, it looks
okay,
good.
Great. Yeah. So if we think about the 2D dilated rotations, so the 2D rotations and then also isotropic scaling, since this is a commutative group, we're able to do a change of coordinates so that it just looks exactly like translations. So if we have this 8 here, and then we center it so it's in the center of the image, and then we do some cropping, and then we do that log polar transformation, that change of coordinates, that 8 turns into this image here. And then translating in the x direction gives you a move in the radial direction, and translating in the y direction gives you a move in the angular direction. So that's sort of what I was trying to highlight by saying, if the group is commutative, there's a change of coordinates, and you can basically treat it like translation in a sense.
So I guess the way I would explain it to myself, I think I understand how this might work. And that's that when you do these convolutional things, you're always working on finite or compact domains.
That's right.
And so it doesn't matter that the plane is infinite in extent. It's that you're only taking a small square anyway. And so if you are taking just a restricted section of the domain, it doesn't matter whether the underlying group is compact or it's not, because you're just taking a compact or at least a bounded piece of it anyway.
Yeah, I think that's an important point to highlight. So I just wrote that down for future talks.
Okay.
Thank you.
All right. So now I feel clarified anyway. Thank you.
Awesome.
So I'm going to interject here for a moment. So I see there are more questions, and I have more questions. So Christine has graciously agreed to kind of hang out for a bit after the talk for extended conversations for people who are interested. For those of you who are not, please feel free to drop off with no harm, no foul. And for those of you who are interested, I ask that we take a short, maybe 5 or 6 minute break to give us all a chance to stretch our legs. And then you can just turn your camera off and mute, or leave your camera on if you want us to see you stretching your legs. And then we'll reconvene in 5 minutes or so for those of you who are still interested in chatting with Christine. But let's thank our speaker at the end of the seminar.
Thank you, everyone.
And I hope to see you all who are interested in 5 minutes or so.